Hi Wildcats, this is an overview of Unit 2, Focus Question 1, where we are looking at the characteristics that waves have and their properties. So to start, there's a video linked in the learning resources as well as we watched it in class where they took the pendulum and they filled it with sand and then they put it in simple harmonic motion. And we saw that as the pendulum vibrates back and forth, if then when they move the conveyor belt underneath it, it creates a wave pattern. And so the point of that was to show that objects or matter that are vibrating in simple harmonic motion create a wave pattern. So there's a connection between waves or simple harmonic motion and waves. So a wave is a repeating and periodic, which we know simple harmonic is periodic, disturbance. So when this uh, particle or matter vibrates periodically as it moves through a medium from one location to another. So by moving the conveyor belt, we're showing as if this pendulum were moving from one location to another. And that gives us the wave pattern. So that's our goal here is to see that this simple harmonic motion causes this wave pattern. But let's look at what a wave actually is. So a wave is an oscillation, or another fancy way to say vibration, that results in the transfer of energy. So waves are transfers of energy, energy moving from point A to point B. So in this picture, we've got a little rubber ducky sitting on the water. Imagine you, like the rubber ducky will just sit there, but if you put energy into the water, like say, drop a rock in there, it creates a wave. And so that energy is transferred through the water and that energy is being transferred by the wave. So one thing to understand though is that it doesn't transfer the matter, it's energy moving through matter. So to show this rubber ducky sits here before the wave comes through. It vibrates up and down as the rubber ducky, or excuse me, as the wave goes past it. So this would vibrate down and up with as the energy went through it. But when it's all said and done, the rubber ducky is in the same spot. So it doesn't transfer matter. It doesn't move the rubber ducky left to right. It just causes it to vibrate up and down. So that's waves are energy that transfer energy. Excuse me, waves are a transfer of energy through matter, not a transfer of matter. There are two types of waves we're going to look at. The first are mechanical waves, but later on we'll look at electromagnetic waves. The big difference between these is that mechanical waves require a medium. So what is a medium? A medium is anything made up of matter. It can be a solid, a liquid, or a gas. So in this picture, the medium that the wave is moving through is the water, right? So that's a liquid. Sound is a wave, and so typically sound travels through air. So in that case, the air molecules are the medium. But waves can move through matter or solids like earthquakes are waves that move through. You can also, like if you put your ear on the table and tap the table, you can hear the vibration, the energy, the wave moving through. So waves can move through solid. So anything that is matter can be a medium. Electromagnetic waves, as we'll see later on in this unit, don't actually require a medium. Okay, so now that we know what waves are, let's look at some of their properties. First thing that waves have are they have crests and troughs. So just like since this wave pattern is created by an object going through simple harmonic motion as it transfers through, uh, simple harmonic motion has amplitude, right? The distance from equilibrium to its maximum displacement. And so they have amplitude, and we say a term to describe the maximum positive amplitude or maximum displacement above equilibrium is the crest. The term that we would use to describe the maximum displacement below the equilibrium is the trough. And so crest and trough are just features or locations on the wave, but that describe the maximum positive and negative amplitude. Another characteristic is wavelength. So the wavelength, we saw before that you can have one full cycle, right? When we looked at period, we saw one full cycle. So that same thing applies. If I start at that crest and go through one full cycle, it would be to here. And that is a distance that I could measure in meters. I could get out a ruler and measure that wave. And so that then is the length of the wave, of one wave. But it doesn't matter where I start. So I could do that. I could start at this trough and go up and then all the way back down. and that would be the same. So you can actually move this in approximately, bad drawing, but you can see that these two lengths are about the same, even though it's from trough to trough versus crest to crest. And I could pick another spot on here. I mean, I could do from equilibrium, one full cycle, back to equilibrium. This is going to be the same length. If I move it over here, it's the same length. So a wavelength. So some things to know about wavelength. Its symbol is lambda. So upside down Y, it's a Greek letter. It's lambda, and it is measured in meters. So we would, because it's a length, we would measure it in meters. Okay, so that is wavelength, amplitude, crest, and trough. Those are the characteristics of a wave. There are two types of mechanical waves, transverse and longitudinal. So there's lots of words here, but the most important difference between them is transverse waves are perpendicular and longitudinal waves are parallel. So what does that mean? Well, in both of these pictures, the wave is moving from left to right. The wave moves this way versus this way. And they both move that same way. What's different though is the direction that the medium moves. So in here we have springs. So this particle or this wave, this part of the spring is going down and up. So in this case, the medium or the spring is vibrating up and down, but the wave is moving left to right. So that means they are perpendicular. In a longitudinal wave, right, if I pulled this slinky back and then pushed it forward, we would find that the parts of the spring go back and forward. So in this case, the particles are moving parallel or in the same direction, or parallel to the direction of the wave. So that's the big difference between transverse and longitudinal. Some examples of those. If you watch, these are transverse waves, right? If I take like this particle right through here, you'll see that particle is moving up and down, up and down, up and down. Again, this is a good example of how the matter doesn't move, the energy moves through it. So the energy causes this particle to vibrate up and down, but the wave, the energy is moving left to right. So that's just like with the people doing a transverse wave here, right? The energy causes them to move up and down, but they stay in the same location. The energy moves through them, but they're staying in the same spot. And once again, this is up and down for the particle, but left to right or perpendicular for the energy or the wave. This is longitudinal. So here in this tuning fork, if you ding a tuning fork, the forks vibrate back and forth, and that causes them to bump these air molecules. And so the wave, now these molecules are moving back and forth, so left to right, and that's the same direction as the wave itself is moving. That can be seen really clearly here, where you can see these dark bands moving through. It's no individual dot. Like if you watch this individual red dot, it moves left and right, but the whole time it's staying exactly where it started, right? That's true of this one here and this one here. They just vibrate back and forth, but yet we can see that the wave or the energy is causing, like this line right here is traveling. The energy is moving through here, even though the particles themselves are staying in the same spot. And because this is vibrating left to right and the wave energy is moving left to right, we would say that these are longitudinal because they are parallel to each other. These are just some more pictures of those things that we talked about where we see perpendicular versus parallel. Last thing we need to know about waves is they have speed. So anything that's in motion has speed, right? A car in motion has speed, and they have speed because they cover some distance in some amount of time. So that distance is the wavelength, and the time is the period for that wavelength to pass. So the wave speed is the time it takes for a part of the wave, like the crest, to travel a certain distance. So if you were this bird sitting here, and here's the first crest right at you, you could get out your bird timer and time how long it takes to get to this crest to hit you. And so let's say you time it and it's 2 seconds. Well, you could get out your bird meter stick and measure that it's 5 meters between these two crests. And so now I have a distance and a time. Speed or velocity is distance over time. So I would say 5 meters. It takes a 5 meter wave 2 seconds to travel. to me for the next crest to get there. So if I divide those, that is 2.5 meters per second. I know how fast the wave is traveling. So hopefully that helps as you kind of organize your thoughts around the characteristics of waves. As always, there are the other learning resources available to you if you'd like to review this again.